Okay, so since I don't have any takers on the Q&A, what I've decided to do is a quick clarification on lesson 2, and I'm recording this right now. And what's going to happen here? If I can get this thing on my where to go. Okay, so I'm going to share the screen. Firstly. All right, and I'm going to put my sketchbook up. Okay, remember on the lessons that your first order of business every day is to check chemdoctor.org. Do the assigned lesson that is there, which today is the lesson 2 video. Then take the quiz, hit submit button, and you're done. On MS Teams, please ignore any signals that come up about whether you completed the assignment or not. Once you hit the submit button, after having taken the quiz on ChemDoctor, you are done. Now, one of the questions that came up this morning was about the potential energy difference between the ice cube and the water. So what I'm going to do here is draw us a really big fatty universe. All right, and as I explained earlier, the universe is the system, all right, combined with the surroundings. All right, and we're going to define, and I made a really big box so that we can have a really big inner box. So this is the system, and the bigger box is the surroundings. Okay, and liquid water is out here in the surroundings. And in the box, in the system, we're going to let the system be our ice cube. Now, the liquid surrounding the ice cube is at room temperature, which is like around 25 degrees centigrade, which is, for the Fahrenheit people, that's like, around 75 degrees. And the ice cube, we're going to say, is at 0 degrees centigrade. 0. Oh, shoot. Let me just fix that quick so it's more readable. So it's around 0. Now, actually, if it comes out of the freezer, it's going to be even cooler than that. But remember, the past video, the system here is actually what we call the cold body. And our surroundings, I'm going to put this in red, is what we call the hot body. So we have a body out here which is in contact with the ice cube in here, which is significantly warmer than the ice cube. All right, and what does that mean? It means that, and I'm going to write this stuff down here, that the kinetic energy of the surroundings is greater than the kinetic energy of the ice cube. Now, if you think about energy, kinetic energy and potential energy, all right, if the kinetic energy of the surroundings is greater than the kinetic energy of the ice cube, then the potential energy of the surroundings is also greater than the potential energy of the ice cube. Now, one way to think about energy is as if it's on a hillside. So if this is Mr. Potential Energy up here, energy always moves downhill. And what does that mean? It means that in order to melt the ice cube, that potential energy is going to flow from the surroundings into the system in order to equalize the energy. Because in the beginning, the potential energy of the ice cube, as I laid out down here, is less than the potential energy of the surroundings. All right, we're using a negative sign out here to indicate direction. The energy is going to flow from the surroundings into the system. And what that means is the ice cube is going to gain in energy, right? And as it gains in kinetic energy, eventually the bonds are going to break. And this thing is going to melt into the liquid. After the ice cube has completely melted and you have allowed enough time to pass, the energy of the surroundings is going to equal the energy of the system. This will be true after the ice cube melts and enough time has passed so that the temperature of the system and surroundings is equal. Oh, let me fix that. Sorry. Let me just get this typo here. All right, is equal. All right, and at the point where the temperature of the system and the surroundings are equal, then that means that the energy of both the surroundings and the system are equal. So in the beginning of this problem, the ice cube is at a lower potential energy than the surrounding liquid, and therefore energy moves from the surroundings into the system. That's going to continue until the ice cube is melted and the temperature of both the system and the surroundings are equalized. All right, and with that, I'm going to conclude the video. And I will put this on YouTube and upload the link both onto Teams and onto the Chem Doctor channel.